There was a time when people thought that Earth's crust, or the outermost layer of solid rock surrounding the planet, was one unified mass. However, a German scientist named Alfred Wegener proposed that maybe the Earth's crust was divided up into pieces that fit together like pieces of a puzzle. He called these plates, and at the time, Wegener's theory of tectonic plates was widely regarded to be false. However, today, we know that he was right. The old perception of the Earth's crust being like an eggshell is replaced by Wegener's theory that it was more like a cracked eggshell. And today we're going to be talking about tectonic plates and the boundaries between them in complete depth. Let us begin with the fundamentals of plate tectonics. To start off with, crust is made of plates. The Earth's crust, also known as the lithosphere, is made of solid rock, as we previously mentioned. Each plate can be very different from another one. There are two types of plates, oceanic and continental. Oceanic plates are the ones found below the ocean, while continental ones are the ones found below continents. Oceanic plates are always going to be denser than continental plates. Additionally, plates can differ in sizes. Some plates can be a few hundred kilometers across, and some can even go up to thousands. Next, we will discuss how plates move. Anytime there is a heat source, you have the potential to create a convection current. A convection current occurs when the material closer to the heat source heats up and as a result becomes less dense. When the material becomes less dense, it rises, but as it goes away from the heat source, it becomes colder and as a result sinks. This circular motion creates a convection current, and there's one going on under the surface of the Earth at all times. The core of the Earth, which is almost as hot as the surface of the sun, creates a convection current within the Earth's mantle. This convection current moves the plates above the mantle. Next, we will discuss continental drift. When Wegener proposed his theory of tectonic plates, he also proposed that at one point all of the Earth's continents formed one big continent. This supercontinent, called Pangaea, has a lot of evidence supporting it. For example, the coasts of South America and Africa seem to fit together like puzzle pieces. Additionally, the rocks on each coast seem to form the same pattern and be of the same age. And lastly, the fossils found on each coast seem to match each other. This theory is supported by plate tectonics because as the plates moved over time due to the convection currents, the continents drifted apart and created the landscape we know today. What happens when two tectonic plates meet each other? One of three things can happen. You'll either have a convergent boundary where the two plates are moving towards each other, a divergent boundary where they're moving away from each other, or a transform boundary where they're sliding past each other. We will provide more details on each of them as we go. At a convergent boundary, one of two things can happen. You will either have a subduction zone or a collision boundary. A subduction zone occurs when a dense oceanic plate meets a less dense continental plate, and due to the difference in density, the continental crust will go above the oceanic one. At a subduction zone, we see three types of features: earthquakes, trenches, and volcanoes. An example of a subduction zone can be found at Mount St. Helens, where the Juan de Fuca plate goes underneath the North American plate. The other type of convergent boundary is a collision boundary. A collision boundary is when two plates of the same density, so two oceanic plates or two continental plates, meet each other, and because neither is more dense than the other, they'll buckle against each other and begin to fold upward. The type of landform we commonly see at a collision boundary is a folded mountain. The second type of boundary is a divergent boundary where the two plates move away from each other. At these kind of boundaries, the features you can expect to see are mid-ocean ridges, rift valleys, volcanoes, and earthquakes. Divergent boundaries were especially important for supporting the theory of plate tectonics because a scientist named Harry Hess discovered that at the mid-Atlantic ridge, which is a notable mid-ocean ridge, the closer he went to the middle of the ridge, the younger the rock was. The only explanation for this was that the two plates were moving away from each other, and new material from the mantle was rising and then cooling to fill in the gaps in between. We call this process seafloor spreading, and it is the process by which new seafloor is added at a divergent boundary. The third and final type of plate boundary is called a transform boundary. At a transform boundary, the plates are not moving away from each other or towards each other, rather they slide past each other. This creates a great amount of strain on the rocks, and as a result, when the energy is released, it causes a great earthquake. The features that you will find at a transform boundary are fault lines and earthquakes. In conclusion, the Earth's crust, or lithosphere, is a solid layer of rocks surrounding the planet. This crust is divided into plates, some of which are oceanic and some are continental. The oceanic ones are more dense. At the meeting of two plates, three types of boundaries can occur. A convergent boundary, where the plates go towards each other, a divergent boundary, where they go away from each other, and a transform boundary, where they slide past each other. Thank you for watching today's SciNOW presentation.